Welcome again to Basics of Noise and its Measurement. Today is the last day of this week, and we will complete this week's journey by actually helping you all understand as to how you can physically measure impedance of a material using a special apparatus known as Kund's tube. So that's what we are going to discuss today. And this whole course is about noise. We have already covered some of the important basics of noise, and now we have just started sharing information as to how different parameters of noise can be effectively measured. So what we are going to learn today is how you can use this apparatus called Kund's tube, and using this apparatus you can measure the impedance of a material. And down in this course we will also actually get to see several instruments and see how they operate, but the first parameter we are going to learn in terms of measurement is impedance of material. So what does a Kund's tube look like? So this is Kund's tube. So Kund, so he was a scientist, and he studied noise and sound, and he was the person who designed this methodology and apparatus, so that's why it's known as Kund's tube. So essentially, in a very simple form, the tube is nothing but a long hollow tube, and at this end you can close it with a material with unknown impedance ZL. Let's say that impedance is ZL, but we do not know, so we want to measure the value of that ZL. Okay, so you place that material at the end, and let's say this position is x is equal to 0, and then you somehow figure out a way to measure this material impedance. There are two more things in this tube. So it's a tube. At one end you have this material, and then you have a microphone in the tube. So what does a microphone do? It actually measures the pressure fluctuations due to sound. So this is a microphone. And the interesting thing about this microphone is that the tube is so designed that it has a slot on its top. So this microphone can move in this way, travel. So it's a traveling microphone. It can travel along the length of the tube. It's a traveling microphone. That is why this apparatus is also known as a traveling microphone impedance tube. And this method to measure the impedance is also known as traveling microphone method for measuring impedance. Okay, so this is a microphone, so that is the second element. First element is the tube, second element is the unknown material, third element is microphone, and then the fourth element is a sound source. So you can have a speaker placed at this end of the tube, okay, and you can excite this speaker using some source. Okay, so that's all this apparatus is about. It is a long tube. At x equals 0 they place the unknown material with unknown ZL. There is a traveling microphone which measures the sound pressure level at different locations, and that sound is generated by a speaker which is at the other end of the tube. Now let's figure out how we can, using this apparatus, calculate the impedance of this material, which is right now unknown. So we will start with what we learnt in the last class. So we had learnt that at x is equal to 0, ZL is the impedance, then ZL can be expressed as Z naught times 1 plus R divided by 1 minus R. This is something we had learnt in the last class. So if I can calculate R, then I can calculate ZL. So now we try to figure out how do we measure R, how to find R. This is the question. Okay. Now ZL can be a complex entity because this specific characteristic impedance we had discussed and defined that it is the ratio of complex amplitude of pressure and complex amplitude of velocity. So whatever is the complex amplitude of pressure at x equals 0 and complex amplitude at x equals 0 of velocity, if we take the ratio we will get ZL. So what that means is that ZL and R are complex entities. They have a real part and an imaginary part. So we have to figure out what is R. But we know that R can be complex. So we will express R as some magnitude, which is the modulus of R, and it also has a phase, which can be expressed as e to the power of j times eta. Okay? So the magnitude of e to the power of j times eta is 1, so that does not influence the magnitude, it only tells us about the phase, and R is the modulus of R is the magnitude of R. So this is equation 1, this is equation 2. Third thing, this is a one-dimensional tube, so any sound which propagates in it will follow the transmission line equation for pressure. So the expression for complex pressure Pxt, so this is not the real pressure but the complex pressure is nothing but P to the power of P plus E minus j omega x over c plus P minus E j omega x over c E j omega t, right? And we know that P minus equals P plus times R, and this is same as P plus times magnitude of R e to the power of j eta. So we put this back into this equation, so what we get is P plus e to the power of minus j omega x over c plus, and instead of P minus we put this expression, so I get P plus times magnitude of R e to the power of j eta e to the power of j omega x over c e to the power of j omega t. Okay, and I can rearrange this, so I can bring P plus out, so this is E, and I can also take E minus j omega x out. So in the brackets I am left with 1 plus magnitude of R, and then I have exponent j 2 omega x over c plus eta e j omega t. This entire term, this green term, is nothing but complex amplitude of pressure. Because what is complex amplitude? Complex time entity is what? It has a complex amplitude. This entire thing is complex amplitude times e j omega t. So this is P of x and omega. So I can rewrite this as Ej omega t, or I can rewrite this above expression as P of x and omega complex amplitude divided by P plus equals this long complicated expression. Okay. So this equation is coming directly from here. It's coming directly from here. Now what I do, so this is my fundamental equation. And what is our goal? Our goal is to figure out the value of R, in terms of the readings made by the microphone, because we can use the microphone and find the values of pressure at all locations in the tube. And with that information, if I am smart enough and if I can figure out the value of R, then I can plug that value of R in this expression, this one, and I can calculate Z. So all this thing which we are doing is essentially to figure out a way as to how we can calculate R, which has a magnitude modulus of R and a phase eta. Okay. So that is what our aim is. Now let's look at this term which is there in the parenthesis, and what I am going to do is I am going to plot it on a real and on a complex plane. Okay. So this is my real axis, this is my imaginary axis, and this entire term is 1 plus modulus of R times exponent j2 omega x over c plus eta. So let's say this point is O, and then there is this 1, so I move 1 unit here, and let's say this distance is OA equals 1, and then what about this term? The magnitude of this term is this magnitude of this term is modulus of R, because the magnitude of exponent j2 omega c plus eta is 1. Okay. So the magnitude of this term is R, same as modulus of R, and the phase or the angle of this is some theta. So I make another point AB, and AB represents E j omega x over c times 2 plus eta, where theta equals omega x over c times 2 plus eta. Okay. So this is there. Now the value of x in this Kunz tube, it could be anything. At x is equal to 0, it will be 0. At x is equal to different values, it will have different values. So what that means is, so actually I am going to draw this line a little shorter. So this is B, this angle is theta. So what that means is, what I was saying is that x can have all sorts of values. What this means is that this theta can vary between 0 degrees to 90 to 80 to 170, so it can vary and it can go in circles like that. So what that means is that this vector AB can, depending on the value of x, it can follow a circular path. Okay. it can follow a circular path. Now again, OA represents 1 and AB represents this whole complicated thing, modulus of R times EJ 2 omega x over C plus eta, and the angle theta can be anything and it will vary with respect to x, okay, and my total vector is, so if I use my laws of vector mechanics, then OB equals OA plus AB, right. Now we are getting close to the thing. Now what we see from this picture is that maximum value of OA will be when the value is when value of theta will be 0 degrees. That does not mean that x will be 0. Value of theta is this. So when it is 0, then there will be some value of x which will correspond to the value of theta being 0. So when theta is 0, then OA will be maximum and its value will be 1 plus, because this magnitude, this radius is r, okay. And similarly, minimum value OA is equal to 1 minus r when theta is equal to 180 degrees or pi radians. Now we define another term and we call it standing wave ratio. So this is rho is equal to standing wave ratio and this is equal to the ratio of maximum value of OA, and the ratio of minimum value of OA. So it will be 1 plus r divided by 1 minus modulus of r. Huh? Oh, I am sorry. Yeah. This, yes, you are right. This should be OB. So when theta is equal to, theta will be 0 at some location of x, and at that location of x the pressure will be maximum, because what does OB represent? It represents the ratio of PXW by P plus, right. So what that means is that this term, when this term is maximum, then PXW will also be maximum. So if I am sweeping the microphone and I find the location at which pressure is maximum, then I record the value of that pressure. I record that value of pressure. So this is equal to P max, that then divided by P min. Okay. So it will be P max divided by P min. So at some value of x, P will be maximum. It will be maximum also at x is equal to 0. It will be maximum at x is equal to 360 degrees, at 720 degrees, and so on and so forth. And P will be minimum at some other location. So if I am moving the microphone in my tube and I find the value of P max, and let's say that P max is 5 pascals, I write it down, and then I move the mic again, and at some other location I find the value of P is minimum, I write that, let's say that value is 2, so then I write down that value. So in that way I can find the value of rho using this experiment. Once I know rho, then I can calculate the modulus of R in terms of rho using this method, using the travelling microphone method, and in this way the value of modulus of R will be rho minus 1 minus rho plus 1. rho is equal to P max by P min, and this is determined experimentally. Okay. So now I have figured out how to calculate modulus of R. Now the other thing which I have to figure out is how to calculate eta. Because once I know eta, I have already figured out how to find modulus of R. Once I figure out how to find eta, then I can know what is the value of R, and then from R I can go and back calculate the value of ZL. So that is what I can we'll do. We'll figure out now how to find the value of eta. So again, how do we find out eta? What we do is that we again sweep the mic, okay, and this so now let's again think about this. So this P min, condition for P min, what will be the condition for P min? Condition for P min will be when this entire thing, this entire term 2 omega x divided by c plus eta is equal to 2 omega x by c plus eta, and because x is in negative direction, see, because our tube, this is x is equal to 0, this is positive x, so this is negative x, right. So x will be negative, x is going to be negative, and let's say at, so when this value is equal to minus pi radians, so suppose I am starting my microphone from here from the fixed location, and then I keep on moving it and keep on moving it until I see that P has minimized. So at that location, let's say that distance is d. So then I replace that x by d, and I actually call it d min, right. So experimentally I measure the value of d min. I already know the value of omega because I know what kind of frequency I am generating in the speaker, and this value minus 2 omega d min divided by c plus eta should be equal to minus pi. Okay. So once it is this, then I can calculate eta equal to omega d min 2 minus pi. So again here d min is determined experimentally. So I have determined experimentally the value of eta using d min. I have figured out how to calculate modulus of R. So now I know the value of R, which is nothing but modulus of R times ej to the power of eta, e to the power of j times eta, and from this value of R I can compute the value of Z, which is the impedance of ZL, which is the impedance of the material which we are interested in, and in this way we can calculate the value of material's impedance. And so this is what I wanted to talk about today. You have learned how to calculate the value of impedance, and we will continue this discussion the next week also. And now going forward we will start actually seeing actual instruments, and we start learning practical techniques related to noise measurement. Thank you very much and have a great day. Look forward to seeing you next week. Thanks.